Okay, so good morning. So this is talk about beer foam. What started out as a Friday afternoon experiment several years ago with Manolis, who's currently an assistant professor in Eindhoven University, technical university, and we tested many beers and looked at the. I was hoping that this would be the perfect introduction for my interfacial rheology talks. That Belgian beer was going to be stabilized by protein films. But you'll see it's more complicated, but at the same time very interesting. All right, how did I come about it, and why did I look at beer foam? I have friends, believe it or not. Professors do have friends. We were part of a tennis club, and we were the worst tennisters of the entire club. And so nobody wanted to play with us, so we got together, and we all sucked really badly. Coordination is not my best skill, and so we form a team and compete, and even started getting better. And one, I'm always the reserve, so and I can't go that often. But you know, we're not the world's best athletes, as you may indicate from this picture. But we're sponsored. We're sponsored by beer, Witcup. Why? Well, the brother of the main brewer is a member of our team. That helps. So this is Thomas Slagmulders. He knows I'm showing him. Slagmulders is a family from Ninove, and they've a family brewery, like medium size, it's not a microbrewery, in Ninove, which is in the middle of nowhere, between Brussels and Ghent, the old industrial heart of textile industry. For those of you know, literature, Daams, the books on abuse and socialism coming up in Belgium was all there. Brouwerij Slagmulders, so Thomas is Slagmulders, and this is where they make this beer. And so Thomas, I was talking about my research as I could not retain myself. I wanted to share the excitement. And I talked about foam and how cool interfacial rheology was. And Thomas said, you know, we actually, to see how the fermentation is going, this is an artisanal brewery, they have equipment and they do analysis, but they just open the kettle and look, and if it's foaming and the foam becomes stable, they know the fermentation has gone on long enough. And I'm like, that's not trivial. So we started looking at it, and then you find, we did a literature search, I'm a believer in Feynman's principle, so you first do, and then you read the literature, and then you learn more. But we did, and there's a lot of work by a person called Bamford from, I think, Australia or the UK. I mean, anyway, and he's written a lot of good papers and also a book on that, etc. And this is from his book. Of course, civilized countries like a good foam head, like Belgium. And in the UK, they would say, no, we don't want that. You're ripping us off. You're not giving me the full pint of beer. I want the. Anyway, it's, you know, again, like our beer foam. Also, we like the beer foam to do this, which is called lacing, and it's a sign of quality. It's a sign of a very stable foam. So foam stability is viewed by the brewers as a sign of quality of their brewing, okay? I already gave you this. I got interested and tried to get the Westvleteren beer. Remember the hydrophobins, so there's stuff there, the gushing. And we'll look today at beer in a little bit more detail. We'll look deep into the glass, which is a good thing. All right. I think most people here are aware of food and know more about this than I do. But beer brewing process, you get barley, you malt it, you mash it, you get the wort, and you boil it. And then after you transfer this hot hopped wort in a fermentation kettle, and you let the magic happen. And then you filter, and you allow for aging and the formation of carbon dioxide in, again, civilized beers. I mean, I think we talked about nitrogen in foams. That's Guinness. Is that beer? I'm a bit obnoxious about Belgian beer. I apologize. Yeah. Anyway, and you can do this fermentation twice, or you can do it three times. You can do the fermentation on the bottle, and so it's all good. Okay. So from a material perspective, what's in it? There's a lot, right? It's a very complex mixture, as most food components are. You have polysaccharides, you have multivalent ions, it's a mess. You have hop acids, which are a bit oily. You have lipids, and what is believed to be, this is in the literature, most important for the foam stability are the proteins. You have lipid transfer protein 1, cool name, and even cooler, protein Z, like World War Z, zombie wars. And those are the two most predominant ones. You can have hordeins or these hydrophobins sometimes appear, but these are, and they're of course influenced by, this is known by number of fermentation steps, by the process, the temperatures, a lot can go. All right, when we look at the foam, we have our protein Z and our LPT1. What happens is they, as the bubbles of carbon dioxide form in the beer and the bubbles rise, you get an accumulation by advection on the surface, and then you get a foam that contains a lot of these proteins. And then this foam is first a wet foam, where you get drainage, and then you can get a dry foam, where the dry foam then breaks, okay? So what we'll try to think about is what happens in these thin films here between the bubbles, okay? So the rate determining step in coarsening of foam is the hydrodynamics and the breakup of these thin liquid films, okay? And so this liquid film has, of course, a lot of forces happening there. There's hydrodynamics, there's flow, so you have velocities, so you will develop pressure gradients. You can have surface stresses developing with all the complexities that you have, and then you have this joining pressure, which is the some of the molecular interaction forces acting across the film. Van der Waals will try to destabilize, steric forces or electric forces will try to keep the things apart. So this joining pressure can be thing. But this is important. Manolis and I did what we know, which is a little bit of fluid dynamics and rheology, and we focused on drainage and film thinning, okay? So we basically will take a deep look into what happens into this film. How does this film get thick? When you have a film like this, we've heard about Joseph Plateau's border. He was looking at minimal surfaces and area to volume ratios and doing mathematics of that, and used soap films as a equivalent, and we call these corners here the plateau border. And the plateau border then dictates a certain curvature, so there's a Laplace pressure in the film, and you have a thin film region, right? And this thin film gets thinner and thinner and thinner as the film goes down. And it's a multiple time and multiple length scale problem. It's very hard to do with numerical simulations because you have to cross orders of magnitude. We did. I won't talk about it because we have some issues with convergence. But we go from, you know, these millimeters down to nanometers, okay? So we're really at the edge of continuum mechanics, okay? Good. And what are these pressures and what are the sizes in bubbles? So these are measurements where they did statistics on really a lot of foams. This is a paper from the early 90s. And you see that these are the diameters of the bubbles and the prevalence of them. And you go from about, the smallest bubbles are about 20 micron, and the bigger ones are 800 micron. The bubbles get formed by heterogeneous nucleation predominantly. So you have either junk in your beer, or in some glasses, like those of you who know Duvel, devil, the beer, they actually scratch the glass in the bottom to have a nice bubble train from the center. So it's so you can. I always give it when I give a class of physical chemistry. I give it as an example, and that it's at 11 o'clock in the morning, and the student who gets the answer right gets to drink a Duvel, which is at about 10% alcohol, so they have a happy day. Yeah. So, but sizes are 20 to 800 microns. Corresponding to that, you have differences in Laplace pressure. The small bubbles have pressures on the order of several thousand Pascal, not huge, but very different from the big bubbles, several hundred microns, where you're in the 100 Pascal range. So if we can probe the drainage dynamics in a range of 100 to 1,000 Pascal, say, we'll be looking at the dynamics, and that should be good. Okay. What is happening in the beer foam here? This is actually Westmalle at 10x magnification and delayed a little bit. You see that there's this bubble shrinking clearly by diffusive transport. You see a pop. There's a coalescence phenomenon. All these things change the shape and the area per volume of the system. So I will have shear deformations, I will have dilatational deformations or compressional deformations. I'm reducing the area per unit volume as I have coalescence. So the resistance to these deformations will dictate stability. Okay, good. So first, let's look at some beers. Here's the Westmalle Trappist, but I could have shown Carmelite, another Belgian beer that gives you the same. And we'll compare it to beer from Switzerland, Feldschlossen, which is brewed in close to Basel. They use it with, make it with Rhine water, and it tastes about the same. And this is what you will see people drinking like half-liter cans on the trains in Switzerland. It's not a pleasant smell, to be honest. And then there's Hopfab. This is Swiss German for Hop. Hop is head. Fab up is off with your head, which is what they should do to the brewer, as I already told. And this is a single fermentation beer. This is a typical Pilsner. And then this is a triple fermentation. Okay, we'll do a very simple experiment. These are Manolis's hands. He will just allow for some carbon dioxide to get into the foam. It's not a very well-controlled experiment, but you will get the idea. We speed up the thing. Here you see the Westmalle. Here you see the Feldschlossen. Here you see the Hopfab. Okay, so let's do the experiment again. You see that the liquid first drains. I first get a drainage flow out of the foam. So the liquid is flowing down through this porous bed of bubbles, and then the foam becomes dry and coarsening. So how does the interface influence that? First, the interface sets a hydrodynamic boundary condition. So if it can carry stress, the flow down the foam will be a flow like in a rigid channel, like in a tube. If the interface only has surface tension, it would be a plush flow, and it would be much, much faster. So a first thing that will determine how fast the foam will drain is what's the nature of the boundary condition? Is it like a rigid interface, or is it a simple interface that only has surface tension? Second, the foam then is dry, and then I get molecular forces acting, and this will also, determine stability. And the drainage flow will slow down, and I have several tools to again slow the drainage down, and we'll see how that works. Okay, so these are the processes. I have drainage initially, right? I have the liquid accumulating at the bottom. Sorry, I'm missing. Yeah, so I have the liquid accumulating at the bottom. You see it, that process is about the same in time scale. And then the long-term stability is dramatically different. So I have drainage, I have coalescence, and I have Ostwald ripening. We will mainly focus on these two processes where hydrodynamics is the main factor that we can influence, and we'll try to understand what happens. Okay, good. So that's what we try to mimic, huh? So we'll design an experiment where we have the equivalent of a thin film between two bubbles, where we can control the pressure jump to mimic the differences in pressure that exist in a foam. In a foam, I have bubbles of 20 micron and 800 micron, so I have pressure differences up to 1,000 Pascal. So a thin bubble will have a bigger pressure, and that will squeeze the film that it has with a thicker bubble down, right? And so I'll try to mimic that in some sense. So that's the setup that I want to have. I want to have a pressure jump across the interface. The bulk stress will be different. And then I want to understand how the interface helps in delaying that. So I have P1 high, P0 smaller. I have a film which mimics the film being connected to the plateau border, and I will look at what happens. So how do we deal with this if it's a simple interface? If foams are just, made of surfactants, and I have no stresses acting on the interface. I have in the blue and in the blue mainly I have almost an inviscid material in the air. In the liquid I have a Stokes flow, and I have a simple shear viscosity of the bulk. At the interface I have a stress boundary condition. These are the bulk stresses, these are the surface stresses, and the surface stress is only composed of a surface tension component in the simple case. So let's assume that. And so I can write down a non-dimensional number. I could probably use the table there. I just say the viscous forces must be balanced by the forces coming from the interface. And when I have a simple interface, that's only the Laplace pressure. So I have a capillary number that tells me how the viscous forces are able to change the film by pushing away the Laplace. If I have small bubbles, I will have a big number here. Capillary number will be slow. The film will not drain very fast and will not be deformed. If I have larger bubbles, that will be the case. Okay, good. So let's see, we can do finite element simulations on this. I modify this capillary number, small capillary number, high capillary number. This is a cross section. I pin the film here. We'll see that we can do that in experiments. And then we can do the solution of the Stokes equation with a boundary condition that cannot carry any stress. And at low capillary numbers, you see that there's just outflow of the film. But because the velocity, of course, varies with position as I get to the edge of the film, because of simply conservation of volume, the material has to accelerate. So I get a lower pressure here. And at higher flow rates, at higher pressure differences, I will see that the film deforms. And you get what is known a Mexican head or a dimple, right? And so this is what I expect. If we look at the capillary number, what goes into the capillary number is viscosity, surface tension, and size. Okay, so we did the three foams. The sizes are the same because we made the same foaming agent. We had a porous film, and we also looked, the bubble sizes are about the same. So the only differences that I could have in the foam are viscosity and surface tension. Okay, so let's measure that. We can take our foams, and we can do pendant drop. In this case, we take a drop, absorb, we wait, and we do it properly. No stresses, no strains, just a Laplacian fit. And what we see, Hopfab 49, Feldschlosser 47, Westmaler 46. It's the same, okay? If I look at the viscosities, we use our very fancy Anton pariometer to measure something close to water, which is very close to the threshold double wall cuvette, and you get viscosities that are the same. We measured the disjoining pressure, the stability, the proteins, and essentially they're the same. Okay, so they're a bit repulsive due to the static effects of whatever is in your things. So everything that goes into stabilizing systems that are simple is the same. So there must be other factors at play. Okay? Right. So what can be at play? A lot, right? This is, again, depending on your view on life, a good thing or a bad thing. But you can have, if you have nothing at the interface, it's going to be a stress-free interface. If you have an interface that has surface active matter, it may be able to carry stresses. How? By Marangoni stress, by surface rheology, surface viscosity, surface viscosity. Proteins may gel, and then you can have that. And so there can be effects also in the bulk of these films. There can be interfacial transport, effects of curvature, and surface rheology. So there's a lot that goes on in these films. And so we want to basically understand that. For the protein film, for the beer films, there's not so much in the bulk. We already see from the viscosity, it's only a few percent higher than water. There's not a lot going on there. So what we see as differences in stability must come from the interface. Good. So how do you study that? There's different approaches. People have done experiments where they take droplets or bubbles in a hydrodynamic Stokes trap, and they bring them together. And they try to see, are in microfluidic devices. I think Denis, if he's here, no, he left. But he did experiments where he decelerated bubbles and allowed them to approach. Or you take a Stokes trap, that's like an optical trap, but you can flow focus with, you can really bring droplets or bubbles together and see how they coalesce, and that's here. Or you connect a droplet or a bubble to an AFM tip, and you approach it to a wall, and you study the drainage dynamics. And so Derek Chan in particular in Australia has done beautiful work then. A very simple experiment that has learned a lot is just what is called a rising bubble, where you just, and I think Vivek has done some work with that as well, where you have a bubble that you just allow to go to the surface, and then from the top you study the thin liquid film and how it evolves by interferometry. The disadvantage is it's a narrow range of capillary numbers. We use a technique called the thin film balance, which is developed by Shelutko. I'll give the reference in a slide. He was in Sofia. It's a paper from 1967, one of the most beautiful papers to read if you do interfacial science. It's called thin liquid films. It has a lot of the ideas that we do. The only thing that we changed from Shelutko's work is that we can regulate the pressure across the film. And so, yeah, what we do is we make a setup, and we have a thin film that we make in an orifice, and we can control the pressure on that. And then we'll see how, here I am again with my favorite slide on interfacial rheology. We see how the bulk stresses, which will be, there will be differences in pressure because the bubble sizes are different, so I have differences in Laplace pressure. I will instate flow, in particular in the aqueous phase, I will have flow, viscous flow, create pressure differences in the film, and then I need to understand how this is, resisted by the interface. And we already know that capillarity alone will not be enough to explain the difference in stability, so I have either Marangoni stresses or I have interfacial rheology to fight the drainage dynamics. And so let's see what happens. So if I make this thin film device, I can have two limiting conditions. One, the interface only has surface tension and none of these terms, and then I would have a plug flow out of the channel. Or if I have like a viscoelastic gel at the interface, I would have a solid wall, and I slow down any drainage phenomena. And so here, again, you see the fluid mechanical simulations. This is a simple film. It drains very quickly. And this is a film with a viscous boundary condition, and it goes already much slower. And also, it's a beautiful problem, because also the way that the stresses develop inside the film depends on the boundary conditions. So you get really strong effects because how the film, inside the film, we see things changing happens. Okay. Again, we won't solve the numerics of this, but we'll just cast these terms into three non-dimensional numbers. We have the capillary number, the viscous stresses over the Laplace stresses. These are the bulk viscosity, water, times the rate of deformation, the surface tension over radius of the bubble. Okay. Then we have Marangoni number, not named after, sorry, but it's the older one, the Italian one, Marangoni, who said that if I have a gradient in surface tension, the surface tension depends on concentration, so the slope of the isotherm over the film radius, this is a gradient in surface stress, and then this is the stress in the film, again, viscosity times rate of deformation. Here is the velocity at the rim divided by the thickness of the film. And then I can have a Boussinesq number, surface viscosity over bulk viscosity times the relevant length scale, which in this case will be the thickness of the film. Okay, so I have three non-dimensional numbers. I can measure surface tension. I can measure how surface tension changes with concentration. I can measure surface viscosity. So I can do that. And so we can see what happens. Okay, but let's first look at the experiments. We made the Chelutko cell. This is a delightful paper to read. It is fantastic, really very clear conceptually, and it has all it really tells you what can go on. And Chelutko made little films and studied them, mainly to look at the quiescent properties, and he used a glass filter with a hole that was drilled. With microfluidic methods, you can make that a little bit more advanced. So we make a bike wheel. Again, Belgium's known for three things: chocolate, beer, and cycling, right? We just got the Olympic champion in the time trial. Very proud of that. And we make a bike wheel, which is a little hole of 0.5 millimeter to 2 millimeter, connected with spokes that drain the liquid symmetrically, so that if I apply a pressure jump on that thin film, I can drain the liquid. And over which pressures? 100 to 1,000 Pascal would be great, right? And this is what it looks like. It's then connected to a chamber, and so I can control the pressure here, and I can control the pressure on the outside. We put the whole thing in a thermostated, thermostated thing where we have temperature, humidity, etc. And then we study with interferometry how the thickness profile evolves over time. Okay, and we can measure the pressure. Initially, we had a very complicated system. I really spent too much money on this, to be honest. We had a very complicated pressure transducer and pumps, etc. Now, if you use these microfluidic controllers for like L-flow, they work perfect and they do the right thing. You don't need more, and they're not that expensive. Anyway, good. And initially, we had to drill the holes, and we would break a chip, and one chip was 2,000 Swiss francs. So for Friday afternoon experiments, it was getting to be a little bit painful. But now we can laminate this better. Anyway, good. All right, so this is what the setup looks like. We have the little, I'm sorry, it's a bit dark. We have a kind of a bit of a special microscope not to get vibrations, but it's just classical interferometry. We can also do capacitance measurement and get a little bit, but it's really, really simple. Okay. And yeah, more pictures. Okay, good. And so how do we do an experiment? We load beer that we have degassed and let come to equilibrium into our holder. it will wet the holder. The holder is made to be hydrophilic on the inside, hydrophobic on the outside, so that we pin the film at the contact line. So we get a film which has an initial Laplace pressure of about 40 to 50 Pascal, depending on the beer that we use. Then we apply a pressure jump. How much? Well, I already told you, 100 to 1,000 Pascal. And then we see how the film drains. And what we measure is the pressure as a function of time. That's what we apply. What we measure is the height and the radius of the film. And we see how it evolves. And so this is for a thing. And here are typical data. You have the radius of the film, which initially, you push, the liquid thins, and then in the center of your film, you get a planar film, which may dimple as you proceed, but it becomes progressively bigger, and the radius, this is the thickness of the film. You initially thin the film, and then you reach a thin film regime where the film drains gradually. And so these are the observables from the experiment, right? And we get them from interferometry. Sometimes it can be a little bit more complicated. This is a Westmalle double, which has a lot of protein aggregates, so it can be hard to reconstruct the phase map, but it's essentially, like in Switzerland, we're used to reading topographic maps. This is in Zermatt, which is a very nice skiing resort, Suniga. It's a train, and then you can ski here and fall down and hurt yourself, as I also do. As I said, I'm not very well coordinated, but this is good. All right. Good, so let's now look at our beers. Westmalle, Rheinwater, and Hopfab, okay? And we apply a pressure jump of 100 Pascal. So initially the film is thick, on the order of a millimeter. We apply the pressure, and then boom, there they go. So you see, Hopfab grows very rapidly and breaks. Feldschlossen grows and breaks, and then Westmalle grows the slowest, but will also break, okay? So how are these films different? So now let's look observant. Do we see a dimple? Okay, here a tiny dimple, right? The film is a bit darker in the center and brighter here, so it's actually a bit thicker in the center and brighter here. Here, clearly you see the Mexican head profile. It's running away. It's not staying symmetric. And that's usually a sign of Marangoni. We blame Marangonis for instabilities. I'm so sorry, right? And the second thing we can look at, how do things move in the interface? Not a lot. These proteins stay. Yes, go ahead.
Here you created your film and then you let it relax and you apply the pressure.
Yeah.
How do you apply the pressure?
Just by a pressure pump. So we have a differential pressure that we can apply. So we know the pressure inside the film, and we can either pull or we can push. Okay. So you do a differential pressure over the film. No. So we have an initial curvature. So there is an initial pressure of 50 Pascal. We allow that to come to equilibrium. And then we apply an external pressure, typically on the gas phase, but you can also pull. It doesn't make any difference. We were a bit worried about dissolved gases. No. It doesn't make a difference. Anyway. So you see that we get the radius, we get the thickness profile, we get also insights into the mobility, and they're already quite different qualitatively. Look, there's some texture, some grainy texture in this Feldschlossen. These are thicknesses of 20, 10, 15 nanometers. So these are really the protein and the protein aggregates that we're starting to see. And in this case, they will form a gel, right? So we did many of these experiments. So this is the drainage time as a function of the applied pressure in the thin film balance, okay? So Manolis made a film, allowed it to come to equilibrium, then applied the pressure step, and just measured how long it took to break. And this is the time as a function of pressure. Again, Belgian beer wins. Most stable. Feldschlossen is not so bad. And then Hopfab really is the one, which is consistent with what we saw macroscopically when we just made the foam and watched the macroscopic stability. So it seems that we're picking up the right thing of these films, okay? And so, yeah, we have done many beers. And so we can compare. Also, we have more information than just the time. We have the entire thickness profile. So if we take the average thickness profile as a function of time, we can compare with predictions for mobile interfaces and stress scattering interfaces. If I have an interface that is really solid-like, I can go to Osborne-Reynolds and use the Reynolds drainage equation, which tells me what it should be. And then if the interfaces are what is known as to be partial, I don't like the word mobile interfaces. For me, it's about stress carrying capacity, and we'll see that. That's because it's a stress boundary condition. But yeah, the literature is what it is. So here we have different things. So here you see the prediction of a stress carrying interface, height averaged over the entire center region as a function of non-dimensional time. In the non-dimensional time, we use a capillary time scale. And so you have height versus time, stress carrying, stress free. And you see that Hopfab is kind of in between. Feldschlossen already tries very hard, right? It's typical for the people from Basel. They try, but they're not as good as the people from Zurich. Anyway, and then we have stress carrying capacity in Westmalle. So this really comes close to the prediction of Reynolds, right? And okay. And we did this, of course, for different pressures. And it agrees, what we see here agrees with the macroscopic stability. So the thin film drainage, the hydrodynamics of what happens in the thin film goes, yes, Vivek? So this is in the thin film region. So this is really, we define time zero, which I should have said, this is what you're asking, is as the point where we see the first interferences. So it's say 600 nanometers down to 20 nanometers. So this would be, thank you. Yeah, good. All right, so let's see what causes this. We can, clearly they're different, and the difference is in the thin film drainage. So the interface characteristics and how it influences the mobility or the stress carrying capacity of the interface is key. So we already have everything for the capillary number. We measured viscosity and surface tension. We need to measure surface viscosity and viscoelasticity. Boussinesq can be a complex number. And then we have the Marangoni number. So to measure the Marangoni number, we need to know how the concentration changes affect the surface tension. So we diluted our beers with Evian to have some ionic, and then we measured the surface tension as a function of the concentration dilution. And so you see that there is a difference, right? So this is the Westmalle has a steeper slope in the concentration range that will be relevant in the experiments. And the other beers are a bit less, okay? And so we did that just by doing pendant drop and Wilhelmy plate measurements. We can also measure the surface rheology. We put beer in this cell and we allow for the proteins to come to the interface, and we do linear viscoelastic measurements. And then you can see here the surface moduli, G prime and G double prime, is a function of time. And we see Hopfab is in yellow. Feldschlossen develops quite some viscoelasticity. And here you see a time scale of hundreds of seconds. And then in the Belgian beers, much to my chagrin, there was no freaking surface viscoelasticity. So very disappointing. And you see nothing. Also, you never wait 1,000 seconds to finish your beer in Belgium. That's another thing, which is good. All right. But yes.
How do you explain the difference in this measurement of surface tension compared to the pendant drop?
No, it's the same. I mean, yeah. This is pure water. This is the this is the concentrations here are more or less the same. It's in the 40s. Yeah, okay. Yeah. Sorry. Okay, so we did some more experiments, more pressures to look a little bit more in detail, because we now assume that these guys, Feldschlossen and maybe Hopfab, may have viscoelasticity. And if you look carefully in the range of our experiments, the time scales, Hopfab is predominantly a bit more viscous. Feldschlossen is already a bit viscoelastic. Westmalle doesn't do anything. But Westmalle is the most surface active of them all. So there's a small difference, and in particular in the slope. So let's see. We do the experiment at identical capillary numbers, pressure jumps of 100 Pascal, and let's look now again. Again, Hopfab goes faster. Feldschlossen, okay, slower. These are two Trappist beers. Clearly, you have the Mexican head, very homogeneous film, and you see that the Mexican head top starts to walk around. Yeah.
With these viscoelasticity measurements, is that a bulk viscoelasticity?
No, that's a surface. That's a surface viscoelasticity. It's done with this double wall ring, where we really, have a subface of beer that's sufficiently large. We allow absorption of the proteins, and we start measuring. Okay, and so this is after having poured the beer. This is how the viscoelasticity at the interface develops. So for Hopfab, we get after 200 seconds of viscoelastic interface. The Hopap is a bit later with Feldschlossen. With the triples, we don't see any viscoelasticity. Yeah. Okay. So if we now think about the fact that these two have surface viscoelasticity, viscous or viscoelastic, it kind of rationalizes that they are not really moving, and we even see a structural evidence of what is causing the viscoelastic nature. This is the protein network. These guys really, if you do these studies on foams made of soaps, you will see the same as what you see in these beers, okay? And so we get here an interface that barely moves. We get very symmetric drainage. That's a signature of viscous and viscoelastic things. With the triples, that's a signature of Marangoni, okay? And we did that at higher stresses, and it will be even remarkable. With Hopfab and Feldschlossen, you will see films with a lot of aggregates that are really not moving. And then as you go to triple Carmelite, you will start seeing instabilities and motion, right? So I'll play these movies over and over again. So for Hopfab, we start draining. We see that it's a relatively planar film. There's a little bit of intensity difference, but it's quite black, so there's no dimpling. There's really a planar film. And if you look at the aggregates, they're moving very, very slowly. Here, you see the film even grows, and the aggregates are immobile, right? They're really not moving at all. If you then look at the triple Carmelite, you see the dimple, and then we start moving around, and here you even get recirculation across the films. So the surface in Carmelite and Westmalle does not have a lot of surface viscoelasticity consistent with what we saw. So things can move around, but this does not mean that the interface is not carrying stress. It's carrying stress because it has a Marangoni stress acting. Yes?
But at the end, the films don't have the same color, so is the film thickness?
Yeah, at breakup, this is a good question. So breakup, the final breakup is still an open question. I will come to that. It's a very good point. Okay, good. Good? All right. So again, Feldschlossen interfaces are immobile or stress carrying, even at high capillary. Dimping is somewhat suppressed. Hopfab, you see you get a transition to partial mobility. And here you get the typical recirculation and movement, which does not mean there is no stress, but the stress is of a different nature. It's a capillary stress. Okay. So again, we can look at this in more detail. Here's the Reynolds equation. So it predicts the change of the height in time as a function of the applied pressure, the internal disjoining pressure in the film, which is thickness dependent. And then we have the bulk viscosity, the film radius squared, the thickness to the third power. And then this parameter alpha is dictating the mobility or the stress carrying capacity of the interface. And again, you see here Westmalle at these higher capillary numbers, it's dead on. For Feldschlossen and Hopfab, you see that there's reduced resistance against this, okay? And so we can characterize this. And so we can map out the mobility factor as a way to characterize the stress carrying capacity of the interface, and we'll use that later on, okay? So yeah, if we then look at the dominant non-dimensional groups, and you fill in the numbers, you see that here the Marangoni number will be much, much larger than 1, order 100. Here, the Boussinesq numbers will be much, much larger than 1, and the Marangoni numbers will be small. So we can at least categorize what goes on. Okay, good. We wanted to do this a little bit more systematic because the differences between the beers were a bit too big. So we contacted Westmalle, and they have from the same fermentation series, they have beers that have single, double, triple fermentation. So this is the Westmalle Extra. That's the beer the monks drink at lunch. It's only 4% alcohol, so the monks are not consistently drunk, so that's a good thing. And so we actually had to ask for it to be shipped because you cannot buy it in the supermarket. They only did, but they were so kind as to send it to us. Then if you ferment it double and you don't filter, you get a dark beer, Westmalle Dubbel, 8% by alcohol. And then triple fermentation, you get to about 10, 11, sometimes 12%, depending on how old the Westmalle bottle is. So these are serious things. If you have a few of them, you're very happy. But they are systematic. So let's look. First, drainage at low pressure. See, again, very similar to the Hopfab. You have some partial mobility, And we'll see that this one also has surface viscosity. I mean, I didn't. Then if we look at the Westmalle double, you'll see essentially an almost immobile interface. There's even a bit of contraction of this. Westmalle triple has been filtered. It's a transparent beer. You get again this Marangoni indicative dimple walking around in the film. If you go to higher stress, it gets more beautiful. Look, partial mobility here. Oops. You get the gel-like structures here, and you get the dimple walking around here. So dramatically different. So how cool is that? Here you have a partially viscous interface, a viscoelastic interface, and a Marangoni interface, just going higher in fermentation. Okay? And so we measured all of them. We did, again, the lifetime studies, drainage time versus pressure drop, surface modulus. Again, the message is that there's not a lot of viscoelasticity. Westmalle Extra has a little bit of viscosity. And then we also did proteomics, of which I know nothing, so I have to use the authority arguments by the experts in our lab. But it shows that, which is not so unexpected, the protein denaturation increases with fermentation steps. And so our thinking in terms of structure is that in the single fermentation beers or the Pilsners, the proteins are there as globular things. And they are essentially two-dimensional suspensions that make things viscous. When you denaturate them a bit more, they expose bits of their hydrophobic parts and they start to form networks. And you really see viscoelastic networks forming. And then when you denaturate them even more, they break up into little chunks that are essentially acting like surfactants. And so that's what we see. All right. Why is this important? We are kind of forced to go away from the workhorses in chemical industry were cleverly designed, right? So typically you had fluorinated surfactants that worked very efficiently. Why? Because they had very strong Marangoni stresses. We cannot use them anymore. So now beer teaches us that we have three strategies to stabilize foams: through viscosity, viscoelasticity, or through Marangoni stresses. And so anyway, sustainable surfactants. So we try to see if we can mimic what we see in the beers with artificial materials. So to mimic Marangoni, we used a surfactant that Nicky Denkov has studied a lot, C12E8, a polyoxetylene ester, and it's also been characterized in a lot of detail by Lynn Walker and Shelley Anna. And so we can really do that. We just absorb it from the bulk, and we expect this to be a classical surfactant, maybe a bit of surface viscosity, but predominantly Marangoni. Then we have our fatty acids, hexadecanol, again, simple molecule, which is again well characterized. All the information is known, and based on the, what has been measured, we expect this to act like a viscous interface. Not very surface active in the traditional sense, but we've seen it as the model material that we characterized in the interfacial rheology reactor. And then for surface viscoelastic, we use the materials of Cécile Monteux, polymer multilayers. There really we have viscoelasticity. And then we did the thin film drainage experiments. Okay, and you will see these are not slowed down, but you see the surface viscous shows a relatively symmetric drainage. There's a bit of a dimple here, and it breaks rapidly. The Marangoni one, huge dimple. In this case, the dimple doesn't walk around yet, but and then the surface viscoelastic, planar film, no dimple, and exerting the stresses, because the stress boundary condition influences the hydrodynamics inside the film and makes the pressure differences less. If we go to higher pressures, it's even more pretty. You get symmetric drainage here. Here you see the Marangoni. We see the dimple again walking around in the film. And then you will see even, not in this film, you may even see the spinodal, the spinodal-like decomposition. And then with the viscoelastic, you really had, at this pressure, a stable film at all, guys. Okay, and so you can scale that. No, it doesn't matter. The message is that how does the boundary condition work and which boundary condition works most efficiently if we want to design materials. Yeah, and much to my chagrin, Marangoni still wins. Marangoni is a smart stress because it only starts to work when it is needed. So when you dimple the film and you start locally stretching the film, the surfactants act locally, and it reacts to the surface concentration gradient that is being created by pushing it back. The surface viscous film is not very clever. As soon as it starts thinning, and the viscosity is doing its business, and it reacts to the velocity gradient, and it increases a little bit its stress, but not a lot. So it's working already when it shouldn't be working. It's not very clever. The surface viscoelasticity, I think there's an open room for a lot of design of materials, because we use these polymer films which are a little bit strain softening, and if you would have things that would be strain hardening, you could stabilize films just as well as. But the idea is you need to act local, and that's the message. And if you compare this now to come to Vivek's question on realistic timescales, this is the Newtonian interface, so it really thins very dramatically. The Marangoni stress really, as soon as you start to make the film, it reacts. And the viscoelastic is also, it's half intelligent, and you could make it more intelligent by tailoring the nonlinear rheology of these films. Okay, good. So again, if I have this Reynolds drainage equation, I can grasp all the effects in a parameter alpha, and here's a map where I have exploited my two routes of design of material. I increase the Boussinesq number, and I increase the Marangoni number. And I can make films very stable, for example, surfactant films, by having a high Marangoni number. Or I can make films very stable by having a high Boussinesq number. These are all data from different things, etc. If I have a certain Marangoni number and I increase the Boussinesq number a bit, there's no synergistic effects, right? And this is because of the nature of the flow in the thin film. And so you have this zone of death, and so mixing things to get to a desired effect of foam stability won't work. You really need to go to high Boussinesq or high Marangoni. It's here multiplied with the Beckley number to get a realistic scales. You need to go, red means stable films, blue means unstable films. Sorry, yeah. And so basically this should not be here. So you have stress-free interfaces and stress-carrying interfaces. And I can only get either viscous or viscoelastic stresses or Marangoni stresses. If I start mixing them, one of the problems, if you make the films more viscous, you slow down diffusion of the surfactants, and then you slow down the recirculation phenomena that you need to get the stability of the films. Okay, so that was what I wanted to talk to you about. I've been a bit shorter. So nature has different ways to impart a stress boundary condition, and beer is the beautiful didactical example of that. Higher fermentation beers use Marangoni stresses to stabilize the foam, so they're like soap. Lower fermentation beers, depending on the process, Duvel was also one of them, have surface elastic interfaces. And simple fermentation beers, like Pilsners or whatever, they will have viscous interfaces. And it depends really on the denaturation of the proteins, etc. And there was some work by Carlsberg. They denaturated the proteins even more, and they have beer foam that stays stable forever. And we did it, I didn't include the slide, but it's really an elastic skin. So you see buckling and wrinkling of the films. It tastes horrible because it's very bitter, etc. But yeah, it's a very nice example, I think, to see how surface stresses control drainage. It's a subtle problem because the boundary condition dictates how the pressure and velocities inside the film develop, and it's a stress boundary condition. So, the film does what it wants to do in terms of thickness and radius. It's a volume, you impose the volume change, but how the film does that is totally controlled by the surface stress in a very subtle manner. And even the small differences between the nature of the interface make a lot of that. And beer is the best for the detectives. There you go, right? Okay, this is a poor picture, but this is also part of my lab. It's not in the lecture notes, and Gareth's been there. I think Vivek has been there. Thibaut's been there. So I have inherited a secret pub at the ETH. And so the beer foam research is actually to allow me to have that pub. So this you can. It used to be. It was designed to be an X-ray scattering lab, but we now run it as a pub. And here you see the students happily drinking my beer. All right, good. So that was all. I was a bit shorter, but I guess you don't mind. Thank you. Thank you.